Bienvenidos a un jueves más de Jueves de 3D Printing. Estaremos dando inicio en punto de las 5 de la tarde al tema de hoy, impresión 3D en metal, con un invitado de lujo que tenemos. Así que bienvenidos, estaremos dando inicio como cada jueves en punto de las 5 de la tarde. Hola, ¿qué tal? Bienvenidos a un jueves más de Jueves de 3D Printing. Como cada semana es un gusto saludarlos. Te recuerdo, soy Sebastián Romo, el director general de 3D, el centro de impresión 3D más grande de México, que te brinda la mayor cantidad de equipos de impresión 3D para poder fabricar tus proyectos. Y el día de hoy estaremos hablando de un tema muy especial, muy solicitado por todos ustedes. Así que bienvenidos, un gran saludo a todos los que nos acompañan desde México, Colombia. Tenemos también Estados Unidos, Ecuador. Así que bienvenidos a todos. Y el día de hoy es un gran gusto compartir con ustedes este webinar que hemos preparado, que el día de hoy, más que un webinar, será un estilo de entrevista con un invitado especialista en temas de impresión 3D en metal. Como cada jueves, te recuerdo que estamos hablando de diferentes temas de impresión 3D. Te invito a registrarte para el siguiente. La siguiente semana estaremos hablando sobre cómo la impresión 3D se aplica en la industria automotriz. Después vamos a estar hablando el 29 de octubre sobre cómo prototipar y cuáles son las ventajas de hacer prototipos en impresión 3D. Y para el 12 de noviembre estaremos hablando de fixtures, gauges y muchas aplicaciones más para los pisos de producción en la impresión 3D. Así que vamos a entrar de lleno al tema de hoy. Y para ello quiero presentarles a Spencer Thompson. Él es el líder de Research and Development de EOS Norteamérica. Quiero ponerles un poco en contexto. En el mundo de la impresión 3D hay tres grandes compañías. EOS es una de ellas, Stratasys y 3D Systems son las otras. Y estas empresas han forjado y creado el ecosistema de impresión 3D. Y es un gran gusto hoy tener con nosotros a Spencer Thompson, que pues lleva ya 9 años en temas de manufactura aditiva. Se graduó en el primer programa de maestría de NCSU, Center for Additive Manufacturing and Logistics, y ha trabajado con EOS en muchos proyectos, algunos de ellos en la matriz en Alemania. Spencer, it's great to have you here. Welcome to our Thursdays of 3D Printing.
Hey, it's great to be here. Thanks for having me.
Thanks for accepting the invitation. And everybody, we will be switching for English so we can have a more a conversation flowing.
Thank you.
I know that you know a few words in Spanish, Spencer, but we will do this in English.
I appreciate it.
Y a todos los que nos están escuchando, recuerden que pueden hacernos sus preguntas en español en cualquier momento en la sección del chat o de las preguntas y respuestas, y yo las estaré traduciendo y compartiendo con Spencer para que sigamos conversando. So, first of all, Spencer, thanks again for being here with us. And I want to go straight forward into letting the people understand what it sells and what is the relevance of EOS into the 3D printing ecosystem.
Yeah, so EOS is a German company. We've been around for about 30 years, and we manufacture industrial laser-based metal and polymer systems. And so I've got a little slide that kind of shows just EOS as a whole. Does that show up?
Yeah, we are looking at your screen right now.
Great. Okay. Yeah, so we're headquartered in Munich, and again, we make these industrial systems that can range from 100 millimeters in like build area all the way up to 400 millimeters cube in build volume, again, in both metal and polymer. And we also manufacture the systems around those machines, and then the software, services, and consulting that go with those systems. And I think it's important for EOS, this statement here. So like, we believe that additive manufacturing is going to be provide a crucial part of the future of how we make parts as a society. And so everything that we do is trying to drive the adoption of additive manufacturing into new application spaces, new industries, and just get more and more parts made.
And just for understanding, you have been on the market since 1989, and you went first with SLS or with DMLS?
Yeah, so it was SLS. I think one of the first ones was actually sand, if I'm not mistaken. So we used to make sand castings that those could then be used to cast a metal. But started with polymer and then metal systems. Maybe 20 years ago.
So you have been in front of the line in these technologies.
Yeah, I'm the same age as EOS. So I was also born in '89.
I'm also from '89, so yeah, we are
nice.
The same age. So please continue. Tell us more about EOS.
Yeah, just one more kind of general slide. We've got well over 3,000 systems in the field now. Metals has overtaken polymers, but it was only a few years ago maybe that there was more polymer systems than there was metal systems. And so now metals has overtaken polymers, which is a win for me. And then our gross sales are roughly 350 million. And we have in our headquarters in Munich, Germany, but we have 2 sites over in North America, one outside Detroit, and then our headquarters in North America outside of Austin, Texas, where I'm located. Yeah, I had one more.
Great.
Sorry. Yeah, I think this picture is really cool. So this kind of like shows what the future of manufacturing will look like and does look like. So this is a room in the basement of our headquarters in Germany. These are all polymer systems, and they're actively manufacturing parts for our machine production. And so we produce a lot of parts such as like ductwork and handles and things like that on our own systems. And I just think it looks super cool to poke your head in that room and see all those machines running.
For sure, it looks super cool, and it makes it more cool. Printers doing printers.
Yeah, right. A little bit of a Terminator aspect of it, but
Of course. And please tell us about, we have talked before with the people that it's in the webinar. We have explained mainly how the different additive technologies work, but please go ahead and tell us more on how metal 3D printing works.
Yeah. So it's pretty straightforward. It's based about having, we have fine metal powder, and that powder is then consolidated with an energy source. So for us, we use a laser. There's other ways to use the E-beam or different ways to consolidate the powder. But essentially, this is how it works in the diagram here. On the right, we have our powder dispenser. And so that's where we keep the clean powder. And then in the middle, we have our build platform. It's usually a similar alloy to what the powder we're printing with is. And then on the left, we have our overflow. And then this little piece in the middle is called a recoater. And so the recoater goes over, the powder dispenser comes up, and then we spread a layer of powder over our substrate. And then we use a laser to fuse that powder to the layer below it or the substrate. And then we do that thousands of times, and that eventually will have a part.
And normally, those parts are what size?
Yeah, so again, we have a small platform that is 100 millimeters in diameter. So that's our smallest machine. And then our largest one is 450 cubic millimeters. And so I've seen parts that go all the way up to, to fill that volume and all the way down, even on the same build, which is kind of why it's cool to have really small parts next to big parts. So big range, yeah.
It does. And you were telling us?
Oh yeah, I was gonna see if this works. But there's on our website, we've got a video, and it'll actually show you what it looks like in real life. So you can see here the lasers moving back and forth really quickly, and there's sparks flying everywhere. It's really, I've been in it for 9 years, and I never get tired of seeing it make parts. It's so cool to me. So.
Currently, we're not seeing your screen, but we will make sure that everybody on the webinar get that link after the session. Yeah.
Yep.
So in terms of materials, we understand you can build in metals, but what type of metals? Are the normal metals we use, or what's going on with the materials into metals?
Yeah. So it started out with maybe 5 or 10 metals. So like 10 years ago, we probably had 5 or 10 metals that we printed. This casting grade aluminums, stainless steels, titanium, these nickel alloys. So these are used in the aerospace industry. Those are kind of the core ones for additive. And since then, so now EOS, we have about maybe 30 materials that we've developed. And it's like every month a new one comes out. And so really with us and then our partners and other people in just the additive space, this list of 30, I think, will be 50 in a year or two. And then from there, 5 years down the road, I could see hundreds of alloys possible. So
And so when you're talking about alloys, additive manufacturing works with pure metals or with alloy metals?
So both, yeah. So there's most of the time it's an alloyed metal. So if you look at titanium 6-4, it's in aerospace or medical, that's already titanium 6-4, and then they just make it into powder form via an atomization process. But there's actually some interesting stuff going on with creating alloys in process. So you can blend, you know, if we look at copper and iron, maybe you can blend those two, copper and iron, together in a certain ratio, and then we make the alloy as we're building a part. So that's kind of, you don't see as much of that, but that is also a possibility.
So if you own a machine of metal, you could be able to make your own mixes of material?
Yeah, theoretically, yeah. So,
So
yeah, if you can source it, you can try it out. Yeah.
and by understanding the process, we were talking this before the call. You told me a great rule of thumb that can help everybody understand. And also if you can explain us a little bit more on how the material is made.
Yeah, sure. So in general, we say that if the alloy is weldable, then you could likely build it on our system. And so if you look really close to the parts, you can actually see little weld tracks, it looks like. So we're just essentially laser welding with powder. So that's a good rule of thumb. And then Okay, yeah. So how's the powder made? There's a bunch of different ways. One of them is called just gas atomization. And so what happens is we have a big vat of molten metal, and then that molten metal goes through a nozzle, and then we use gas to kind of disturb it. And just like rainfall, you get little droplets that form, and that's how we get the round metal particles. And that's just one of a handful of different ways to make it, but probably one of the more common ones.
Nice. It should be very fun to watch how
Yeah,
it's made, that powder.
I imagine so. Yeah, probably really hot in there. So
And one of the questions that people makes us a lot, and I wanted to share it with you, it's why to 3D print in metal versus doing it into a more traditional way of machining or other metal methods we already know?
yeah, so that question is essentially why I have a job right now. So we are all trying to figure that out. And so my job and then the team that I'm on is called the Additive Minds team in EOS. And our job is to look at people's applications and try to understand if this is feasible for them to print, how could we make it feasible to print, and then help them through that process. So a lot of times, especially several years ago, maybe it's a little less now as we kind of have a better understanding of additive, we would see somebody that saw 3D printing on a website or news or webinar, and they're like, oh, that looks cool. And so they go to their shop floor and they look for parts, and they find a part. Maybe it's been made on a lathe for 30 years. And then they bring that part to us and say, hey, I want to get into 3D printing. What do you think of this? And can we print it? And generally the answer is yes, but should we? And I think that's the conversation that we have with customers. So a lathe is really good at making cylindrical and round objects. You wouldn't make a block on a lathe, you'd use a mill. And so a 3D printing machine is just another tool like that. So we have our own constraints. Often they're less restrictive than like a traditional fixturing or tooling you'd need for traditional manufacturing. But you still need to take a lot into consideration when you are looking at printing. And I have a slide I can continue to go on about why, what types of things work well for additive. If you
please. And while you share it, maybe you can add the answer for a question that Manuel just sent us. And I think it's very relevant to talk it about right now. Like, how close is intolerance additive compared into machining or milling or the other processes?
Yeah, that's a really great question. So in general, we're not as, we don't have as high tolerances as you would have in a machining process. And there's a lot that goes into that. One of them being the metal powder itself. And so if you look at the part surface, you'll actually, it looks like somebody just threw a bunch of metal powder at a wall. And so that powder, it just gets stuck to the side of the part. And so that's a limitation that we have. There's definitely post-processing techniques that can make that less. But in general, if we're doing a critical part that needs to mate somewhere, there's generally a post-machining or some type of post-processing to hit the tolerances that we need.
Great. So after printing, you can put it into a normal machining and that will make the tolerances.
Yeah, exactly. So, you know, if you look at casting, it's very similar, I think. And so a lot of times the casting will have a post machining or a surface finish cleanup, something like that.
Great. So if you want to share us your screen, that will be great.
Yep. Okay. We all good?
Yeah.
Okay, so yeah, again, when do you print versus when do you traditionally make it? I think you can look at these 4 categories as things that we excel at in additive. And so on the left side here, freedom of design. So if you look at that part and you handed that to a traditional machinist, I think they would tear it up and laugh at you or something like that. So you can't, there's not a lot of ways to make that part besides 3D printing. And so we excel in complexity. And so highly complex parts would be difficult to make in another manufacturing method. And so just highly complex parts, organic structures we do really well, whereas big, bulky block structures, we don't do that well, actually. It's easier for us to make that complex part than it is a big block. And then another category is called functional integration. And so this one is just how can you add in additional functionality to a part without adding more parts or having something else added to it. And so a common application that we see is an assembly. And so we look at an assembly. I have an example later, but it was 248 individual components in a rocket application that were brazed and then machined to one plate. And so we looked at that part or that assembly, and we were able to make it into one part. And so we saved assembly time, we saved cost and lead time waiting for all those parts to be brazed. And we also improved the reliability of the part by removing all those individual welds. And so that's a really big win for us if we can combine things or add functionality to a part we're going to make anyway. Customization, I think this is really an exciting space and kind of highlights the junction between additive manufacturing and the digital space. And so, for instance, I recently ordered a bicycle helmet, and I got it from a company called Hexer, and they print helmets in polymer, and they use our EOS system. But I ordered the part, and then, or I ordered, the helmet, And then I downloaded an app. They sent me a cap, and I put the cap on my head. And then I had a friend kind of scan my head just with my phone. And a couple weeks later, I had a helmet show up at my door, and it fit my head perfectly. And so I think that type of mass customization isn't possible when you have all the tooling needed to make these parts like you would traditionally. And so that space in general, I think, is going to be really exciting to see where it goes, and especially as the kind of digital tools that we need to enable that kind of grow with the additive systems. And then one more, so rapid prototyping, that's where we started. The initial parts we were making 30 years ago were for prototyping. We're still really great at that, again, to reduce lead times. And one thing that I love about it is, if you were doing a casting, you have to design your casting, then you do some analysis on it, send it to a casting house. Maybe the lead time is 6 weeks. It's a complex part. You get it back. If something changed in design or something wasn't quite right, you have to redesign it, send it to the casting house, get it back. So you're just killed with lead time. And so for us, we can take a part and design it for additive, and we can look at it and see maybe there's something it needs to fit into, or maybe there's something we're worried about it building. We can cut it up in the CAD file and then print only little pieces of it, see how it works, and then move on, tweak it, and then print the whole thing. So I think that's a big advantage to additive. It's just the time savings and design iterations is a really big part of it.
Great. And what about examples, or you were telling us a little, we will be later in the conversation with some examples, but people starting to question what industries, what type of parts, any types of industry that takes more advantage into the technology?
Yeah, so from an industry standpoint, the early adopters were medical and aerospace. And so what you see there is low volumes, and so not 1 million parts a year, sometimes in the 1 to 10 parts per year. And then mass customization in the medical space was a big factor of it. So we could create, we could CT scan somebody's injury, say there was a car accident or something, and then we can custom fit a titanium implant to work and fixate their bone, whereas buying something off the shelf wouldn't be applicable there. And then as far as industries that we're seeing now grow, the automotive industry is really exciting. There, we're dealing with much higher volumes and a much higher cost pressure. And so we are really striving to bring down our manufacturing costs and get into the automotive sector. That's a big one that's growing. The electronics industry, and so the copper that we've recently been able to print, that one's exciting. And then I have a few examples if you want me to show actual.
Yeah, please. People is looking forward to look all the examples.
Yeah, so I think this part's really great. So this is for a project with GM. So if you look at the left, it's a seat belt bracket that connects the seat belt to the frame of the car. And so if you look at it, we've got some machined parts, probably some laser cut and bent parts, and all that's assembled together. And so we were able to take that application, and so you look at what kind of loads does it need to hit, you look at what space does it need to fit into, so mounting holes. And then we take this technology as a design tool called topology optimization. And then we can apply the loads that we're expecting to see in operation. And then the computer iterates between, it removes material where there's no load needed. And then it iterates between there, and you can run design examples over and over until you have something that meets the requirement. And so this part, again, I don't think you'd have a tough time making it any other way. It was 40% less weight. So again, in automotive, the gas savings there, stronger than the original component. You have less parts that you need to track. And then it highlighted, again, the ability to quickly iterate. And so 150 designs, I mean, you'd be fired, I think, if you had that many tries at a machined part. So this is a really cool part.
Do you see a future where automotive will change their parts into these type of parts, or efficiency part assembly, etc.?
Yeah, I do. And so right now, we're starting to see it on really high-end automotive, so high-end cars, because just the cost is still probably prohibitive for most mass-produced. Like you won't see it in a Toyota Camry right now. But we are actively looking at and developing new powders and new methods to new parameters to build parts with those powders that speed up the process. Larger machines with multiple lasers. So we have one machine with 4 lasers that can improve the cost of the part. And so eventually I do believe that we will get there, just because with the numbers like that, I think if we can make this close to the same price, is just, it's not much of an argument, I don't think.
And what other cases or examples you can tell us about?
Yep. This one's really neat. So this is an airspace. It's a hydraulic manifold on an A380. So the part on the left, we looked at that, and it's a fairly typical manifold for an aircraft, I believe. And we looked at the assembly around it as well. And so we were able to see the part and see how it fits into the aircraft, and then combine parts that are directly around it. And so I eliminated 10 parts. 35% weight reduction is huge in commercial aviation. So that's a huge win, because we can, we're just moving hydraulic fluid around in these channels. But there's a lot of it that's just there because it would be too costly, or you can't machine away the block. And so we're only using the material around the channels that we need. And so we get that reduction in weight, and then it's got the same functionality and meets all the regulation requirements too. So this is a really cool part.
For sure it is. And what's the size of that part? It's a very small, medium?
Probably that size, so relatively small component. But I think that we will start to see more and more hydraulic manifolds done this way. It just kind of makes sense. So as long as we can still meet the performance requirements, then the weight savings that we can get from it, I think we'll always win.
So that means if you build something into additive, well, you have the freedom of creating those pipes and creating all those special forms, but it's leak proof?
Yeah. So we're, when we started creating metal components, it was like a sintering process. And so we called it direct metal laser sintering. And so there was porosity there. But over the past, maybe 10, 15 years, we make fully dense parts. So we call it direct metal laser melting. And so these parts are 99.99% dense in some instances. So yeah, fully airtight and can hit the strength that you need for this type of application.
And a part like this, people are just starting to ask, this is a common question that probably you have all the time. How much will cost you to print a part like this?
Yeah, that is a great question. There's just too many factors to say to really answer that correctly. So, depending on the size, how many of these can we fit in a system? What is the volume that they're looking for? So if they're making 10,000 of these, that's going to drive the cost. So it's hard to say, unfortunately.
But for people to understand normally, and correct me, Spencer, what you look into a price of a part printed, first you need to take the consideration of the design and all the engineering that took you to get there. Then you will have the hour rate of using that machine, no matter if you own it or you are using a service bureau like us for print. Yep. Then you will need to pay for the materials, all the post-processing. So there are many factors that drives up the pricing for metal 3D printing.
Yeah, it's true. And so that's why, the four categories I talked about earlier, you really need to make sure that your part, you need to print it, first of all, and then that you're adding value somewhere else in the life of that part to make up, because it is more expensive relatively than a machining or maybe even casting operation. And so the costs are coming down, but it is a tough argument to directly transfer apart from a mill to an additive system. But when we can add in these optimizations for weight or stiffness or performance, and we can add in reduced assembly time and improved performance there, then you start to be able to make the case that we should be printing the part.
Yeah, that's what we always tell people. Like, if you're building blocks, it's better price competitive doing in a normal milling way. But if you're doing specialized parts or parts that had been into foundry, then to assembling, milling, and different stages or processes, when you consolidate into one in additive, the cost will be more effective than the other methods.
For sure, yeah. And so it's a really complex, process to try and figure out where all the costs are going to come from and what that in part will actually end up costing you. And I think we've done a really good job with our consulting divisions to try and make sure that we encapsulate all of the surrounding the cost that might go into it, so our customers understand what they're getting into, and we can maximize the outcome.
And for people watching us, also costs into additive depends on the size of the part. You can have small parts costing you $100 or big parts costing you thousands of dollars. So it depends in the geometry. So there are a lot of things that run the pricing into metals. And do you have any other example or applications you want to show us before going into the next question, Spencer?
Yeah, I had one more that I think we can talk about real quick. Medical. So I mentioned medical earlier. It was an early adopter, and so Ti-64 implants, they've been printing those for quite some time now. And this is a spinal cage, and so this would be inserted into somebody's spine, and then the vertebrae would fuse into this part, and then allow them to have a better life experience, basically. But I picked this part because it shows kind of some uniqueness and some unique things that you can do with the systems that maybe aren't all the time talked about. So if you looked at this part and how you would traditionally make it, you've got this solid inside, so this shiny area. So that maybe would be cast or milled out of titanium stock. And then you'd have another operation to add to this porous structure around the inside. And so you'd have a sintering or plasma spray type operation to have that structure. And then on the top, you see a different type of structure, so kind of more of an organized grid. That would be another operation. And so with additive in metal, we can do all this at once. So as we built this part, we tweaked the laser parameters, and we created these unique structures and surfaces at the same time that we made the part. So just from there, we've already eliminated several production steps.
And at the end, basically, the medicals go and put it into a patient, and that's it.
Yep. Yeah. So and in medical too. So has been a lot of research done in these porous type structures that I show here, and we can create novel structures that you can't make any other way. And there is evidence to show that these improve the way the bone grows into that structure, and actually we're improving on just how you would make it traditionally already. So that's pretty cool space.
It's really a cool, actually, people are starting to ask that if you can share more about that type of application. We will share it after. So we are going through different questions that people has been asking us. One of the question from Andres: how long will it take to develop a new metal alloy for specific customer, specific application? He puts the example that, for example, you have stainless steel or 316L, but if somebody wants to develop 420 steel, what will happen for that type of applications?
Yeah, that's a great question. So, I lead the North American R&D team in metal here, and we develop new alloys and new parameters for those alloys. And again, a lot of times the answers in 3D printing are it depends. So again, it kind of depends, but we've had alloys that we really believe are weldable, castable. We believe it'll be easy to develop those parameters. Maybe we can turn that around in a month to get some starting points to start making parts. And then we've had some other alloys that are more difficult for us to manufacture. And that, we've had projects that last, 6 months to a year. And it also depends at what level are you looking for that development. And so if you just want to make prototype parts or get some parts, you just want to be able to print something, that's a low technology readiness level. But if you're looking to get into a regulated space like medical or aerospace, then we need to control the supply chain, the feedstock of that powder coming in. We need more robust parameters. We have to prove that they meet the mechanical requirements of the application. And so that adds time, cost, another level to develop a new alloys.
That's very interesting to know. And continue, Miguel is asking us, that this question will feed into this, that what are the requirements for a material to be capable of being used in MA technology?
Yeah, so I think physically speaking, the powder needs to be small enough that we can spread it. It needs to be able to spread. And so there's certain powders, like if you did a ball milled and create little flat powder particles, we can't really spread that with our recoater. And so that's a limiter. And then the size, we're using a 100 micron spot size laser. And so if we have bigger particles than that, then we won't fully fuse those particles together. And so we have a certain particle size distribution that we look for. And then other than that, again, like we said, weldable is generally a good rule of thumb. So some things like ceramics or refractory alloys aren't currently producible for us, but as we look into higher temperature machines, things like that, we'll start to get into the higher melting alloys as well.
Great. And the last questions for materials before moving to the next topic. It's possible to 3D print parts with alloys or combinations between metal and plastic powders?
Yeah, so not with our technology. Yeah. So we generally have one type of material in the system, and then the whole part and the surrounding structures are made of that one material. There are people that are looking into dual materials, but that's not super common.
I know that EOS, because we use that material for some of the parts of our customers, the Alumite, it's basically a nylon 12 reinforced with aluminum.
Yeah, that's a good point. Yeah, actually, we have on our polymer systems, we can print a polymer, I guess it's a polymer matrix composite, but yeah, so we have metal in that polymer. So technically, yes, you're right. Yeah, we
but it's more into the plastic side than in the metal side.
Yeah.
And I think we're running out of time, but this question, I believe, is the great to close the Q&A from the people that assist. Don't worry if we didn't get the time to answer your questions. We will be answering them via email after the conversation. Jose Juan is asking us, do you think that one day AM will replace the traditional manufacturing methods? What do you think about it?
No. Yeah, so I don't believe so. And so what we'll see now in the next 10 years is we'll see applications we will take some applications from traditional methods. But like I mentioned with the tolerancing and stuff that we can get out of our machines, we won't ever be able to have something that mechanically makes, well, can't say ever, but in general, there's things that traditional methods do way better than us. And additive manufacturing is just another tool at our disposal to create parts. But almost all the time you see a combination, right? So we have a post machining step or a post surface finishing step, something like that. So it's another tool at our disposal to create parts, but it will not replace traditional manufacturing.
So it's only a way to fulfill things that can't be done before, new opportunities, new geometries.
Yep. Yeah. So there's going to be a ton of stuff that we can do that traditional can't. And so, yeah, I think we'll take some of it, but if you look at the numbers or something, we're like 0.1% of all manufacturing. Maybe it's 1%. Yeah, so we're a small chip out of traditional manufacturing.
Yeah, we always say that additive, well, the manufacturing industry will be the full pie. Mm-hmm. And basically additive will be like a little line over there into that pie chart.
Yeah, and eventually, like we want to see that grow, but there's just so many things that you can make that are, just fit perfectly on a traditional machine, and we're not going to take any of that.
No, and it's cool how things are going. And our final question to end up this webinar is, what's the future for EOS into metal?
Okay, nice. Yeah, so cost, I think, is a main focus to us, and to bring our costs down to get into some of these industries like automotive, like consumer electronics or consumer goods. We need to improve the productivity of the system. And so we're doing that with bigger systems, with multiple lasers, with streamlined turnovers. And so our newest machine, the M300, is a 4-laser system with a really streamlined turnover process to improve our build rates. So that's kind of on the system side. And then on the material side, we're looking at new, faster production processes. We're looking at different lasers. And so can we expand the size of the laser spot that we're using? Can we build a thicker layer? So all of that stuff is going to feed into bringing the costs down. That will make it easier for people to start with additive and easier for these cost-sensitive industries to really buy into additive. And so that, I'd say that's our goal.
That's amazing. And we hope every day metals are more approachable, and I'm pretty sure they will be.
Yep, me too.
Spencer, thank you very much. In name of all the team in 3D and all the attendees, thank you for joining us on this webinar.
Yeah, thank you for having me. It's been great.
No, and this is your house. 3D is always open for great knowledge as the one you have shared with us today. So thank you. And I hope to see you very soon. And I will be doing the goodbye in Spanish, but thank you very much, Spencer.
I will say one thing. I live in Austin, Texas, and I've still never been to Mexico. So let's find me a reason to get down there. I want to come visit. So.
You will find the reason very soon in 3D. You will see it.
All right. Thanks so much.
Thank you very much, Spencer. Y a todos por acompañarnos. Muchas gracias. Ha sido un excelente jueves. Creo que fue un tema de gran interés para todos ustedes. Gracias por todas las preguntas que estuvieron haciendo. Me despido no sin antes recordarles que como cada jueves los estaremos esperando aquí, y desde 3D, ¿cómo podemos ayudarte a utilizar la impresión 3D en metal? Pues bueno, número 1, compartiéndote espacios como estos, pero aparte te ponemos a disposición nuestra gran capacidad de manufactura aditiva, entre ellos equipos en metal, plástico, resinas y diferentes tecnologías que pueden ayudarte a producir tus proyectos de una manera muy eficiente en los mejores materiales, y estamos aquí para ayudarte y guiarte a través de todo este camino, como lo hemos hecho con muchos clientes a través de México y Latinoamérica. Principalmente nuestros servicios de impresión 3D te podemos ayudar con todas las tecnologías, metales, plásticos, como te platicaba. Y pues te recuerdo que como cada jueves estamos aquí hablando de diferentes temas de impresión 3D y cómo la tecnología está cambiando la manera de fabricar en el mundo. Así que gracias por acompañarnos. Yo me despido dejándote una encuesta de salida para que nos comentes qué te pareció el tema de hoy, y espero con mucho gusto verte la próxima semana en nuestro tema de impresión 3D, que tendrá que ver con las diferentes aplicaciones en el mundo automotriz. Bueno, de hecho es en 2 semanas. Así que gracias por acompañarnos y te espero la próxima. En nombre de todo el equipo, te deseo un excelente fin de semana y nos vemos el próximo jueves.